So I'm going to walk through the build of my first ever scratch built VTOL, mostly focusing on the airframe, the hardware. Software is ArduPilot with a bunch of customized parameters, but more or less ArduPilot. So I just flew this VTOL from hover to fixed wing flight for the first time. 3 months ago, I had no experience designing and building VTOLs or even planes or drones for that matter. So I've done this all in the last 3 months. And yeah, managed to getting a very solid hover and transitions well into fixed wing flight and transitions back, which I'll link to the video as well for that. When I started designing this 3 months ago, I had a subscale model, a full scale model, sorry, of a 2-seat eVTOL I want to build at a later point, but this was just, those model requirements basically helped me shrink that down as the basis for this one. So that helped me with, like, for example, sizing the wings. So like wingspan is 1.2 meters. The mean aerodynamic chord is around 165 mils, with obviously that tapered wing, so it's much wider chord, longer chord at the roots and much narrower at the tips. But sizing the wingspan was exactly 1/10 of what I would expect that full scale model to be. The weight estimates ended up around 2.5 kilos. Just for something of this size, with all the components that I looked into, ended up sourcing, that was my estimate. And then of course I had to size the propulsion, both in lift and in forward flight, fixed wing flight, to actually be able to carry that 2.5 kilos. At the time I started this, I wanted the easiest way to basically start and build a VTOL with no experience, and came across the Armin Wing technique for building foam RC planes, and that looked like a great approach. Definitely drawbacks with that approach for VTOLs, but that's what I found at the time, and so I followed, or I just used a bunch of guides on YouTube that I found for Armin Wing building, and that's how I ended up with this foam fuselage material, which is really cheap, very bendable. As you can see, this is folded over one piece of foam for both wings, and you know, if you look at the wings, they're relatively smooth. This is a very I mean, aside from some poor taping on my behalf, but and then a few creases here, but more by and large pretty smooth wings. It's very light tape, this white tape, and then this tape is a heavier white duct tape that I've used just to reinforce. So you can see I've capped these ends. These are 3D printed pieces I used much later, once I could actually 3D print. The ailerons are hinged. You can kind of see up through there, that hinge, so that they end up having pretty decent control throw, and they were able to bank pretty stable with good stability at about 45-degree bank angle, going yesterday during my fixed wing flight at about 44 miles per hour, 70 k's per hour, so it was quite good. The fuselage is probably one of the bigger challenges with the Armin Wing in terms of aero. Like, you know, you're basically looking at a box, and you can see here I had a pretty high drop. This thing survived about a 4 meter 12-foot drop, and it ended up creasing quite a bit, but relatively strong, so I'm glad for that. But yeah, you can see very unaerodynamic. You've got the hatch here for flight controller and avionics wiring, which I'll show you later. This nose was like the third nose I've used. Initially it was a foam nose, but this was 1 for aero and 2 for fitting a smaller battery as far forward as I could to balance the center of gravity. And this is made with foaming PLA 3D printed material with very light infill. So this nose actually ends up being significantly lighter than the already light foam nose that I had before. And the tail of the fuselage, I tapered it, as you can see, which is better to allow more airflow, air intake into the pusher motor, pusher propeller powered by the pusher motor. And you can also see the carbon fiber little rods there, which are basically wing tie down mounts, which as part of the Armin Wing process, you basically use rubber bands to tie down the wings. That ended up being one of the big problems with the Armin Wing design for VTOLs. So I had to actually 3D print a custom mounting plate to connect the wings to the fuselage, which is inside here. It's hot glued down, and I need to keep flying this. I won't open this right now, but I can add a photo to this video afterwards. But basically, the Armin Wing is, the rubber bands don't provide clear signals back to the flight controller as to what's happening with the attitude of the wing, the boom, and the motors. And so the flight controller wasn't getting the right inputs to actually then correct the stability of the VTOL in hover. At least that's what I think happened. After I mounted after I used the PETG 3D printed material mounts, it was much more stable than hover. I didn't have those tuning issues I had before. One of my biggest problems I had with the transition and just getting this into a full forward fixed wing flight was this pusher prop is mounted too low. Why is it mounted too low? Well, it should be mounted as close to the vertical center of gravity as possible, but given all of the weight in the motors in the tail, you really need this to be a bit higher, especially because I switched from a heavier battery to a lighter battery to try and increase the thrust to weight, just to try and hit a minimum airspeed to go into fixed wing flight. But yeah, as you can see, it's mounted quite low there, and so when this motor spins up to transition from hover to fixed wing flight, basically the whole VTOL pitches up, right? And then because the center of gravity is higher, it creates this nose up pitching moment, whole thing tilts up. And so it's wasting a lot of energy trying to climb when all I wanted to do is just to accelerate as quickly as possible and to hit that airspeed that's higher than stalled airspeed, basically. So to fix that, I had to make several changes. The hardware change I made here was to tilt down this motor slightly. You can kind of see that it is slightly tilting down, like maybe 2 or 3 degrees, not a lot. I didn't want to pull out the whole mounts and assembly for the motor, so I just basically tried to bend the aluminum mounting plate a little bit more and hot glue it, hot glue the plate, which you can kind of see up here. Okay, so the tail I chose to be a inverted VTOL, sorry, because with a pusher prop like this, you want the airflow coming off the pusher prop, the thrust being generated, to actually have clean air and not have it be, you know. So if you look at the positioning of that, you don't want the wing, the tail to actually be in the way. And so the inverted VTOL was one of the better choices for that. Again, foam with the PETG 3D printed mounts I ended up doing later. And then also a mounting piece up here. Okay, you can see I've also used 3D printed PETG here for the motor mounts. I had purchased some aluminum motor mounts, but they weren't tight enough for these carbon fiber boom tubes, and yeah, they just weren't as actually rigid as these PETG ones, which I just made when I had very little CAD skills, but they work pretty well, very secure, they won't move. The motors and props sizing was basically based on estimated weight. You need enough thrust in hover and also takeoff landing to have just enough control authority in pitch, roll, and yaw. And that usually means about 2x thrust relative to the weight. So you need about 5 kilograms of thrust, and these four motors roughly do that. So we've got servos electronically controlled by the flight controller, managing the control surfaces, right? So here it's a ruddervator. It's a combination of a vertical rudder and a horizontal elevator. Probably needed a little bit more angle on this inverted VTOL, but so far the yaw control by the ruddervator has been fine for the turns. One benefit of inverted VTOLs is you get pro versus yaw, so the way the ruddervators move during rolling maneuvers actually helps with you roll and doesn't work against it. Yes, so the servo wires and the motor wires, they all run into the wing, which I won't open because it's all glued down. Like I said, I want to still do more test flights. And then through the wing into the fuselage wing, the central wing section here, which then runs into the fuselage. And then I'll show you here through there. Oops. You can get a view of all the wiring through there, which are the motor wires for motor power, as well as the signal wires for the ESCs, which are the inverters that convert DC power from the battery into phased AC power, rapidly switching AC power for the motors to control RPM for the lifting motors, and also for the pusher motor. Another drawback of the Armin Wing design is that for VTOLs, which I didn't really know because I hadn't seen any Armin Wing VTOLs online, I just kind of used it even though I didn't know if it was fully going to work. Another drawback is that because of the way the wings mount to the fuselage, it's quite hard to get the rigidity that you need for a strong and steady hover. And what I mean by that is you've got the booms coming into the wing here. You know, these are 3D printed sleeved boom mounts in the wing. I've got another one of those like here for 2 spars that run through both wings, and then are tied down, mounted down. When I wasn't using PETG, when I was the 3D printed mounts, this is the underside of the wing and the underside of that mount, because yeah, it just simply wasn't rigid enough, and so any RPM changes to the motors during hover was just causing stability issues. You can also see just the servos here controlling the aileron. That's just cut out of the wing and glued in like that. So with the avionics in this thing, you've got just a Martech F405 VTOL flight controller. These are all the servo leads, these small wires that servo and signal leads for the motors. These are the motor leads. The thicker ones is the battery lead that connects to battery, which I usually put in the nose to balance the center of gravity. With the center of gravity, it's really important, and something I didn't really think about with VTOLs is you need to balance the thrust center of the 4 lifting rotors. So you can see from, the thrust center is about in there, right? And I've measured that, and it's roughly like about here, right? So you want to balance that thrust center and that line with the center of gravity of the weight distribution in the VTOL, and that's challenging because that means you have to have the forward rotors somewhat forward of the wing, more so than the rear motors. If you notice, my forward motors are actually, I initially put them a bit further back, but I had to push them forward. That way it helps the VTOL to actually hover and not pitch forward or back when taking off or landing. It just gives it more stability. Also means the lifting motors are all using roughly the same amount of energy because they're all carrying basically the equal amount of weight distributed. So this was the battery that I used in the successful fixed wing flight, the first successful fixed wing flight yesterday. I'd originally gone with a battery over twice as heavy and as much capacity as this one, but the thrust to weight when that battery was in this VTOL was just too low. It was accelerating really slowly, and I don't have that much space at the airfield I fly at to actually basically make turns and have it pick up enough speed in a short enough distance. So I need to increase thrust to weight, so I went with this one, which is a perfect size for this because it's big enough that I can get enough minutes of hover time, but small enough that I get as much weight savings as possible. So I save like 370 grams, almost a pound, just by switching to this battery. It's a LiPo battery. It's not the most energy dense. I'll be using a much more energy dense pack and a 6S pack. This is a 4S pack. So higher voltage means less current, means wires can be thinner, or at least have more overhead for wires. But the LiPos do a good enough job for this build, so I didn't need to go with something more hardcore. I had to mount this battery right at the front of the fuselage, so it sits that far forward, and basically I had to do that because again, with the center of gravity, center of gravity had to be forward enough for hover, but also center of gravity has to be roughly between 20 to 30% mean aerodynamic chord, just for like inherent stability of fixed wing planes. Any less than that, and it's a bit too stable, and you don't get as much pitch authority and just generally authority in flight. But if it's too far back, then it's inherently unstable, and you actually you have to do a lot more sophisticated a control surface management to actually make something like that fly well. So for a simple open prop, low speed RC plane, or even a general aviation plane, you tend to have the center of gravity around 20 to 30% of the chord width of the mean aerodynamic chord, and the mean aerodynamic chord's not quite, but just around 50% of the distance from the wing root to the tip. So yeah, it's roughly about here. And in order to get that center of gravity pretty dialed in, I had to have this battery as far forward as possible. But one of the challenges with this build was the way the types of ESCs I use, the types of just the way I designed the fuselage compartment, is that I had to like basically take everything. I had to redo all the wiring, basically open heart surgery on this thing every time I wanted to change the battery, and I had to do that several times. So that was a bit of a pain. Anytime I had to adjust CG, which I had to do a few times. So this GPS unit with a built-in compass is not very aerodynamic at all, obviously, for a plane, but I was getting some some compass interference issues, probably because of when I had mounted it on the top of the fuselage here or here, various different locations, because the battery was positioned here, and when I had the bigger battery, it was a bit too close to the compass itself. So just to be safe, I put it on this mast, which I just grabbed from my old quadcopter. Just cut the mast height a bit, and yeah, I've had no problems with that since. I won't need that on the next build, just for better aerodynamics, but yeah, it just ended up looking like that for this one. And this is the receiver for radio controller, my radio controller's inputs to fly this. Very lightweight, very lightweight. It's cheap and cheerful, it does the job. Like if I wanted something longer range, I would get something with much better antennas, probably something like a ELRS system, but this was fine for my needs. So in terms of the software and the firmware, I used ArduPilot, which I've been using for the two off-the-shelf, so one off-the-shelf quadcopter I built and assembled, and the off-the-shelf VTOL I assembled. You really need ArduPilot for VTOL, but it's really, really good out of the box, like pretty stable hover, even though my hardware wasn't quite dialed in at the start, like I said, with some of those rigidity issues, the yawing issues. But yeah, ArduPilot's great. I customize a bunch of parameters, but yeah, works really well. And on those yawing issues, so when I first started hovering this quad, this VTOL just had some instability in yaw, and so one of the changes I made was just to just tilt these motors inward a little bit, which just improves yaw authority and helps physically provide a yawing moment for the VTOL frame, instead of just purely relying on different RPMs between diagonal pairs of motors. There are many limitations with this Armin Wing technique and also the foam itself. So I'm going to be 3D printing my next builds, fully 3D printed VTOL airframe. I found much lighter motors and ESC inverter setup that will cut a lot of weight. 3D printing will also cut weight, just because this foaming PLA is actually lighter than this foam board. Yeah, and 3D printing will also just cut out the amount of, like, with foam board, if you damage it, then you have to build a whole new one yourself. With 3D printed parts, I'm going to design it myself, and then I can just reprint and then re-glue pieces as I need to. And there's just much less time required to just make more parts. I also didn't use FPV in this build because, again, I hadn't ever built a VTOL before, but I have used FPV before, and I plan to use it for the next build. I also plan to add a Jetson Orin Nano. Yeah, I'm going to plan to add my Jetson Orin Nano. I'm going to take it out of the dev kit. It's got its NVMe storage there. Yeah, so plan to use this on a carrier board in the next build, which will allow for some pretty serious computer vision pipeline work to allow for autonomy features like obstacle detection and autonomous navigation, flight planning. So that should be pretty nice. The next build is really going to be focused on building a 3D printed VTOL and getting as much range as I can and much endurance as I can with it. So I'm going to be maxing out the battery. Like I said before, the battery energy capacity should be about 3x what my large battery, about 6x what this one can do. It's going to be way more efficient in fixed wing flight. It's going to be even more efficient in hover as well. But yeah, the autonomy stack is going to be something I want to play around with as well. Okay, thanks for listening. This was the build of my first ever scratch built VTOL.